Yeah, so I guess now we can get started. I don't think other people will join. Yeah,
Yeah, yeah. I
yeah.
think we
So,
can start.
yeah, good evening, and this is our third session of problem
Only,
solving on fundamentals of electronic device fabrication. So, we'll directly move to this week's questions. Yeah,
sure.
yeah, it will be a continuation of doping, carrier concentration,
Yeah, yeah.
plus a little bit of built-in potential and things like those. But equations, I'll be like projecting the equations, and based on that, you can solve.
Built-in potential when you mean eccentric, extrinsic semiconductors.
Yes.
Okay.
Yeah. So here the question is, a silicon PN junction is formed with donor and acceptor concentration of 10 power 16 per centimeter
Mm.
cube. Intrinsic carrier concentration is given as 10 power 10. What is the built-in potential of this junction? Give your answer in volts. So you have a direct equation where you have to use Na, Nb, Ni and built-in potential V. So if you can
This
check.
is for the fourth week session. Is it with the
No,
junction?
it's for the third week. It's like a continuation. We can't separate it. Like whenever a
Yeah, I
PN
know, but
junction is formed, yeah,
yeah, it's for PN junction. I think
yeah,
this question I
yeah.
have done because this is in the fourth week, right? The fourth week session is assignment submission for 21st or 22nd. I think this week
Okay,
it is only the third submission. So usually I am on dot.
okay.
I'm not ahead. I've not started the fourth week. I think fourth week you'll upload on Friday, if I'm not wrong.
Yeah, this
Nevertheless,
is yeah. So if
nevertheless,
you yeah, if you can, these are the things
yeah,
that
I
are given to
understood
you.
these things,
N
but
A, N D, N I, N T, and you said you had the textbook, right? So
yeah, I
can
have the
you,
textbook. I'm
yeah,
looking at that.
yeah, if you can get the
I
equation
let
for
me
built-in potential.
okay. This might be in the next
Yeah,
junction six.
yeah.
Yeah, let me go there. I don't know. I have not read that book till there. So metal semiconductor junction. It is there, I think.
Yeah.
Let me see. I see an equation wherein it shows delta V.
Not delta V, something like this. Have you seen V0 is equal to KT by E ln NA ND by NI square?
No, PN junction. Let me see. Just a moment.
Yeah, sure.
Yeah, there is one. It's in a chapter after that.
Okay.
That's in the what's this chapter called? PN junctions.
PN junctions, yeah.
Yeah, I'm still not there, but yeah, let's
Yeah.
go ahead and answer that in the interest of this question.
Yeah, basically the only thing is that you have a silicon PN junction, you have an N-type dopant, P-type dopant, and when you combine them, it forms a junction, and the potential will be created across the junction, right? So we are
Huh.
calculating the value of that potential.
Perfect. Yeah,
Yeah, it will
I know
depend
this.
on the donor and acceptor concentration as well as the intrinsic carrier concentration.
So
If
this
you
potential is because of the electrons and the holes moving across
yes,
it.
the charge separation across the junction.
Hmm. Okay. So if it is beyond that, electron will start in the
Yes.
junction area where they're combining, right? The holes
Yeah.
are combining in the PN junction where the gap and whatever gap is there.
Yes.
When they combine, this is the voltage which develops, and when it is beyond that, there is a flow happening. Below that, there is no flow. Correct?
Yeah. So
Okay.
yeah, it's like a direct substitution. So if you see
Hmm.
here, like all these three are the same unit, right? If they are not in the same unit, you will have to convert because it's a denominator numerator kind of setup. Since all of them are in the same unit, you can directly substitute, and
Hmm.
these are all powers. It will get cancelled to some extent, and you can
Hmm.
substitute the
Hmm.
rest.
Yeah, makes
Yeah.
sense. Yeah.
Yeah. Can you just try and let me know what's the answer you're getting?
Yeah, I can do it on an Excel, but
Yeah.
yeah. In the interest of time, I know this is more of substitution and we have to do that substitution. I'll go ahead
Yeah.
and do that. But if we can move and answer the questions which are more technical, where from an understanding point of view,
The
where I
thing
do
is,
not.
I'm asked from NPTEL to get you
Okay.
people to solve. So
Okay.
yeah,
Okay.
yeah,
This takes a lot of time in the sense. In the sense,
yeah.
we waste a little bit of time
No, that
solving
is
that.
the idea that we can get up to time so that it will be helpful for you in the examination.
Sure.
Yeah,
See, am the motive for me is different.
yeah,
Uh,
yeah. But the thing is, like content for a week will be fixed. If we go on with discussing only the concept, like I wouldn't be able to complete the schedule that they have given for me. We'll wind up too fast.
Okay, yeah, yeah,
Yeah,
that's fine. No, no, I'll make sure that we continue till the time, whatever is there.
yeah,
I'll ask you so many questions.
yeah. Okay.
Okay, perfect. We'll go ahead and do that.
Yeah,
I'm just looking for my Excel sheet. Give me a moment.
yeah, sure.
Yes. ND is 10 raised to 16. K is Boltzmann constant, right? Here.
Yeah, Yeah, so these will be a substitutions.
Yeah, yeah, I'm just done. I am taking some time to convert this, not convert, just to put in an Excel.
Yeah, yeah, sure.
Is it 2.262?
0.262 is not there in the options. Here, right? 0.71 will be the answer.
Point
7,
seven.
but yeah.
I lose 1 second. Oh, E is the electron charge here. Okay.
Yes, yeah.
1 second. Let me change that. 1.6 into 10 raised
Oh,
to 19.
minus 19.
1 second. I think that's where the error is. 10 raised to minus 19, right?
Yeah,
Okay, should happen. Yeah,
yeah.
it's okay.
0.70 volt will be the
Mm,
answer. Yeah.
yeah.
Yeah. So next is calculate the width of depletion region for a germanium PN junction. Same, like now the question before we discussed what is the voltage, right? So
Mm,
here we are finding out what would be the width of the PN junction. If this is the PN
mm,
junction, what would be this particular width? And this is the P type or N type of whatever.
mm,
Yeah, here too we'll have to use the acceptor concentration is given, donor concentration is given, intrinsic carrier concentration is given, and temperature is given. Additionally, relative permittivity or epsilon is also given. So an
mm.
equation that involves all of these would be used in case you want to find out the width of the BN junction.
Okay.
Yeah, can you just check in your, like in the same chapter, you'll be finding the equation for width. Yeah,
WO is equal to WP plus WN is there.
yeah, and the expansion for each of these will also be there. Anything for the width, is it given?
I think it is. Give me 1 second. Mm, This is the same equation, right? You showed me V naught,
Yeah,
but I think we have to. Yeah, it's given in
by,
terms of V naught.
yeah,
Width is
so
given in terms of V
can
naught.
you
I
tell
think
me the
the V naught
equation?
is root of 2 epsilon V naught upon E into N A plus N T divided by,
Yeah,
yeah, this one.
this
Exactly.
particular equation. So
Mm.
first, like you did before, you will have to find V
One
naught.
second. Show me that again. Okay. V naught and 2 epsilon. Yeah, that's perfect. Yeah.
Yeah. So
It's
first you have to
written.
find out V naught and
V
then
naught you have to
use
find
that V
and then
naught.
you have to substitute this into that.
Yeah.
Okay. Got it. Yeah, I don't want to do the substitution again, so let's
Yeah.
move. I have not read
So
this chapter, so I'll go ahead
yeah.
and do that.
So V naught part I have shown. Now can you just substitute in the width part that small equation? Like V naught you have done in the previous question, right?
Yeah, I have done.
Yeah. Yeah. So the width part can you just substitute?
Yes.
You should approximately get 0.28 microns, and this is a non-optional question, so like you
Oh,
don't have choices here. So it would be good if you can find, like, try to get the answer. V naught is there, and you can directly substitute whatever is given in the equation for finding the width.
what is the value of epsilon?
Epsilon is given as 16.
16. If you can just direct me on the numbers, I'll type in so that it'll save
Yeah.
the time. V naught
So,
is,
like, sorry,
what is V naught? The number?
0.43.
0.43
Yeah.
divided by E, right?
Yeah.
1.6
6 into
10
10
and
power minus 19.
1. Yeah, 1 second. What is Na, if you can just guide me?
And A is 10 power 16.
16. And Nd,
Is 10 power 18. If it's too tedious, I think we can
no, no,
just,
no problem. 1 second. It should be. I've started it, so I'll go ahead and do. 9.31 into 10 raised to minus 18.
but the thing is, if you see this particular thing, the previous one, we could use the same, like when you're calculating electron volt, if you've noticed in the previous equation. So this come as a ratio, right? So it's
Uh,
okay if you go for centimeter inverse or meter inverse, it doesn't matter. But when
uh,
you are using it for the width equation, here it is a sum and here it is a product.
correct.
So you need the conversion and then you need to do. Otherwise, final answer will be wrong.
1 second. I thought the conversion.
Like, have you done the conversion? If you, or initially itself, you can convert it into the same. Like 10 power 16, you can
Okay.
convert into 10 power 24.
Meter cube. Okay, okay,
Yeah.
okay. And everything is in metric cube. What was the issue? 1 second. Let me read this question again. So you converted it to metric cube, metric cube. So when you wanted in volts, you did this was given in per centimeter cube. So you converted into per metric cube. So why did you do that? What would happen if it was in centimeter cube?
Like the rest of whatever is given you, the Kelvin part of the relative permittivity, everything is in SI units, right?
How do you know that it's not given anything? SI
Like,
permittivity is without unit, right? It's
yeah, but
16 units.
if you see Kelvin and centimeter, centimeter is not the SI, meter would be the SI, right?
Correct.
Yeah, so then you'll have to convert if you're
Mm,
using, because final voltage you are getting in volts, that too is SI unit. So only thing that is not SI here is the centimeter inverse. So you have to convert it to meter inverse.
mm, okay. Yeah, got it. Probably this is a little bit to remember. Okay.
Yeah, of like not only for this question, for all questions, you will have to convert it.
Convert to meter cube. Okay.
Yeah, and one more thing, if you see here, whatever is given to you is the relative permittivity, right?
Hmm.
Relative permittivity is epsilon r. So absolute epsilon will be epsilon by epsilon 0.
Hmm.
So whatever you substitute in the width equation is this epsilon. That is the specific permittivity of that particular material. So
Hmm.
you'll have to multiply your
Relative permittivity.
relative permittivity, that is your 16, with permittivity of free space.
Okay.
Yeah.
Epsilon naught is given or?
Epsilon naught is like a constant. It's a known constant. It will
So
probably
it
be given to you in the like
okay, okay,
formula sheet. You
okay.
can't use 16 directly.
Got it, got it. Yeah.
Yeah,
I think I should go through the chapters. I
yeah.
am 1 week usually behind. I am on the bar. If it is submission for tomorrow, I just do the previous one chapter. So
Okay.
I was
And
thinking this is for the third week's
okay.
problem set. Okay,
And
go ahead.
one more thing I can suggest you is towards the end, that is when we are talking about JFETs, MOSFETs, and those things, it would be
Mm.
better if you can go through the videos and then attend the
Yeah,
sessions.
yeah, yeah, yeah. I'll
Yeah,
do that.
because this at
Last
least,
week it was
yeah,
not like that. I think last week we were in sync.
sync, yeah,
I did the same video and we had the same set of problems. I think this week they have gone to the
yeah.
fourth.
So this week at least, like in the
Yeah,
problems
I
are
will do that.
understandable,
Okay.
but towards the end, that might not be the case.
Sure, sure. I know. I will
Yes.
go ahead and at least go through the videos for the
Yeah,
next
so
week.
if you see here that 16 is multiplied by the permittivity of space, free space.
Yeah,
That is epsilon 0.
got it.
Yeah. So which of the following is or are true with regards to hole current in a semiconductor? We know
Okay.
that electron current is due to the movement of electrons. In similar way, if we interpret hole current is due to the motion of holes in the valence
Holes.
band, right?
Balance band. Hmm.
Yeah. So
No,
in that
I probably
context,
I'll choose.
yeah,
I'll choose. I think I should be able to answer this. Let me go through.
yeah.
It's due to the electrons moving in the valence band. No, it's not. It's due to the electrons moving from one covalent bond to another. No, it's not. It's due to the electrons moving from one bound state to another. No, it is due to the electrons moving across the band. One second. Which of the following is or are true with regard to the whole current in the semiconductor? Note that more than one answer is correct. It is due to the electrons moving in the valence band. No, that is definitely not possible. Electrons moving in the valence band, whole current. Electrons move in the mm, conduction band. It is due to the electrons moving from one covalent bond to another. Yes, B is definitely an answer. It is due to the electrons moving from one bound state to another. Yeah, it's B and D.
Is it like moving across band gap? I would not say that is right, right?
It is, yeah, it has to, right? It is because electron from valence band has to move to the conduction band. That's when the hole is created in the valence band.
Yeah, but that is with regard to creation of the whole, right? But the whole current, like, does that contribute
The
to whole
whole
current?
current is
Yeah.
due to the electrons moving from in whole currents, holes move, right? Electrons never move.
Yes.
These all are
Yeah.
related to the holes, electrons. Then I don't know which one is. It is due to the electrons moving in the valence band. How is that? How is it the
So
whole?
I think like B and C are correct because first we'll discuss that part. So
Yeah,
basically, what happens during hole formation, like electron moves from the valence band to the conduction band, right?
valence band to the conduction
Conduction
band. That's
band.
correct. Yes,
So an electron is added in the conduction band, the hole is generated in the valence band. And
correct. That is correct.
yeah,
Hmm.
and this hole itself, if you see, it can be because an electron has, suppose you have electrons, 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 and one has moved up. And
Hmm.
and what happens is you have a hole, you have an electron and electron. So whenever
Hmm.
these holes move around, we can say that the whole current is like whole
Correct.
current is
Hmm.
happening.
Hmm.
So when this electron moves from its bound state to some another bound state, so
Hmm.
this too becomes a hole, right?
Hmm. Hmm. Correct. That is correct. Okay,
Yeah,
B and C is correct. I was worried
yeah.
about the A one.
I don't think A is correct. I think I've made a mistake here.
Okay, okay,
Yeah,
that's
yeah.
fine.
Yeah, so B and C are
I
the
also
correct
chose,
ones. Yeah,
yeah, C I did not say, but yes, that is
yeah.
correct.
This
Only
is
C.
only because of generation.
Yeah.
Like it doesn't contribute to the whole current.
Okay.
Yeah, it just generates the holes. It doesn't
Got
contribute to
it.
the holes moving across each other.
Yeah, yeah, the
Yeah,
D one, right? You're
yeah,
talking about.
yeah.
Yeah. Thanks. I think
Yeah.
that's good. We can go to the next.
So if the intrinsic carrier concentration in certain semiconductor, this is from like previous week.
Yeah, yeah, this I think I
Yeah.
will do that. Hold on.
So
I will write this.
yeah,
Let me do it on a paper. If
yeah,
I
sure,
see
sure.
that might take more less time, then
Yeah,
I don't know. Let's see that. Excel is taking because I have to enter type.
yeah, and like if you have a physical calculator with you,
Yeah, I'll do that. I'm trying that only now. I have a computer calculator on the laptop. Let's see if it has LAN and all.
yeah,
I'll check. If the intrinsic carrier concentration in a semiconductor Ni okay. Two Ni's at different temperatures are given. Okay.
yeah.
Ni1 is equal to 2.4 into 10 raised to 6. Calculate the band gap of the semiconductor
Yes,
EV.
EG, yeah, EG or EV, yeah,
EG, yeah. Okay. So I think there is an equation. Let me go through that one
yeah,
second. Yeah, this is from a very previous chapter to
yeah.
that. I know this equation is there. Let me directly go there. Something I know. Between 2 Ni N1 divided by N2, there is one equation. I'll just go through that. Yeah, Eg is equal to Ni1 divided by Ni2 T1 by T2 raised to 3 by 2 exponential of Eg divided, no, not this KB. Yeah, this one is the equation. Yeah, I got it.
Can you substitute
Yeah,
inside?
I'll do that. Just a moment. I'll just do it manually
Yeah,
on
sure.
write it myself and I'll 10 raised to 6. Just let me know the value of K. 1 point, sorry, value of both.
1.38 into 10 power minus 19.
Thank you.
Sorry, 10 power minus 23, it's not 19. It's minus
Yep.
23.
Okay, okay. I'm doing the virtual calculator. Let's see
Yeah.
if I'm successful. I think the laptop calculator doesn't have a scientific. Uh, 1 second. Scientific. Yeah, last time I had the same problem. I didn't know how to do the raise to in the virtual calculator.
Okay.
How do that? How do they do? Do you know that?
Let me take my version calculator. So you have an option there like x power pi, right?
1 second. Yeah, I got the scientific also now somehow.
Yeah,
Yeah. I want to do 2.4 into 10 raised to 6, right?
yeah. 2.4 like
2.4 into 10 I put, and I want to put raised to 6.
yeah, 10 power
So
x is
x,
there. Yeah,
yeah, 10 power x is there. Okay, so I directly use that. Okay. 10 power x, if I do, let me try that. 10 power, yes, it's coming. 10 power 6. No, I did something wrong. 2.4 into 1 second. I press 2.4
okay.
and then I press an multiplication sign, correct?
Yes, 2.4 into then,
2.4 into 10 raised to x. I press that button.
but it won't come like that. I think for a gear calculator, how it works is that first you have to press, suppose it's 10 power 6 you want to do, first you type 6, then 10. Then it power 10 to the power 6 it comes.
6.
Then 10 power x you have to press. First you type in
Yes.
6
Yeah,
and
yeah, yeah.
yeah.
10 6, then 10 power x. I
And then
got
you
it.
have to multiply your 2.4 to that.
Yeah, you can do 2.4 before and after. No problem. That's
Yeah.
fine. It'll take. Let me try. Yeah, you can do before and after.
After, yeah.
That's fine. So it gave me that. Then I did divided by. Again, I did a 10 raised to y, and then I do. No, I had to do another way around it. Sorry, 1 second. Let me do. Hit an error. It doesn't give backspace also. Okay, let me repeat it again. Sorry, I'm taking time, but yeah, this will make me better. So you said first you should do this and then press a 6. It comes to
First you press 6 and then you press 10 power x and then it comes the final value. First you
6.
have to type in the exponent.
First I type the exponential and then I directly type 10 raised to 6, 10 raised to x, or I have to multiply, press and multiply signature and then. Yeah, I got it. Sorry. I think that's correct, whatever you said. Some time.
Yeah, yeah, sure, sure. I've just been checking, like I've been thinking about the previous question. I think option A as well is correct. So after we finish this, we'll go back to that.
Mm-hmm.
Yeah.
Yes. How do I? Okay, got it. How to give 10 raised to minus 5?
So you'll
So I
have
tried.
to type in -5 first, then 10 power x.
No, it is not giving. Okay, let me try if it is right or not. 8.56. Yeah, it's correct. It's not giving me LAN of negative number. LAN of negative number is not possible.
Lan of negative number, I don't think so. Lan of negative number doesn't work, so you might have gone wrong with the calculation somewhere, I guess. So, does it go to something like this? Or is the LAN outside? Is that what you're saying?
One second.
There is a minus EG there, but
2.4 into 10 raised to 12.
yeah.
No, it is 10 raised to 6. No, just
Is
go back.
it the units?
Oh, you wanted it in meter square?
Yes.
Oh, shit.
Yeah, but it's okay. I think you got the whole
Yeah, I
idea,
got it.
right?
Yeah.
Yeah,
Okay, but it's a struggle to use virtual calculator.
correct.
Okay,
Yeah.
real struggle. I don't know.
So the
Last time also I had the same problem. I didn't know how to do the 10 raised to y, and I left most of the problems which had that requirement.
okay.
Okay.
Yeah, but this I think this subject like the last course was descriptive, so even if you skipped a little bit of
Yeah,
problems, yeah, it was
here
okay.
I cannot. Yeah, I know.
Yeah. So
Yeah,
okay. So which of the following represents? Okay. So before we move on to that, the other question. Now when I
yeah.
think of it, I feel that option A is correct as well. I'll tell you why.
Just go back.
Yeah. So basically, you have the conduction band here, you have the valence band here, right? You have all these electrons, and this is an like nothing was there. And when once few of these electrons move up, what happens is that in the valence band, we are left with few holes, and there are electrons as well, right?
Correct. Hmm.
So what is an electron current is whenever the electron moves, and hole current is whenever the holes move.
Hmm.
And the holes move, and the direction of these currents are also opposite. So
Hmm.
keeping that in mind, so whenever these electrons move, suppose you have the current flowing between these two. Suppose you
Correct.
assume that, and suppose this electron by something or the other, it decides to swap its place with this hole.
Hmm.
So the next arrangement would be such that initially hole. Now you have an electron here and you have a hole here.
Hmm.
So the new current would be this one, right? So
Correct.
basically, due to the electron motion itself, there is a hole current going on.
Okay.
Yeah, so that is why we can say indirectly the first one is also right. And the reasons for these electrons moving can be due to like bond breakage or from one state or another, like whatever it is, like whether it is a covalent bond or some another type of bound state to another. So whenever there is an electron motion or an electron swaps its place within another electron or a hole, it can contribute to a hole current.
Then what is the electron current then? When
Electron
it moves
current,
in the conduction band, that's also the same, right?
yeah,
When electron move, then what is the difference between a
like
hole current and an electron?
and I like if you see from a like logical point of view, whole current is like a concept. It's not like quantifiable as electron current, right?
Hmm.
It is something that's assumed to happen in the
Correct.
direction opposite to that of an electron current. So whenever there is
But
an electron
it's
current,
still an electron current. That's what you
yeah,
mean to say.
yeah.
Okay. Got it.
So next is which of the following represents the order of increasing carrier concentration? Assume all the semiconductors are at room temperature. So this is like something you'll have to,
Yeah, I know this
yeah,
answer. I
yeah,
have a table,
yeah,
but yeah, which of the following represents the order of intrinsic carrier concentration of
like Ni values.
NI values? I have this table here.
Yeah,
Probably I'll just go through that and I'll tell
yeah.
you.
It's better to keep in mind at the order, like since there are
Yeah, it
only
is,
three.
I think three. It is germanium, silicon, and gallium arsenide.
Yeah, it's increasing order, right?
Okay.
Yeah,
Increasing order is that only, no?
yeah. 10 power 13.
Germanium, silicon, and gallium arsenide.
Like germanium is, yeah,
Decreasing order is the other way around. Increasing order is the germanium, silicon, and then 10 raised to 6 gallium arsenide.
yeah. So this is like the reverse, I guess.
Yeah.
Yeah,
So increasing order, see, increasing order is that same one. So it should be B.
B. Yeah. So change to B.
Mm,
Germanium, silicon, and gallium arsenide.
Yeah.
Yeah, and since these are only three, if you don't remember, like silicon, at
Yeah,
least from problems, we all know it's always 10 power 10. We'll
yeah.
automatically by heart
Yeah,
that.
that
Yeah,
we remember. Yeah.
yeah,
So we have to search for silicon in between.
between, yeah.
Yeah. Okay,
Yeah,
got it.
so next is intrinsic gallium arsenide has a higher resistivity than intrinsic silicon due to one of the reasons mentioned below.
Intrinsic gallium arsenide has a higher resistivity than intrinsic silicon due to one of the reasons mentioned below. So is the most okay.
Yeah,
Gallium arsenide has a higher electron mobility than that of silicon. If the mobility is high, then conductivity is high. No. Gallium arsenide has a lower hole mobility than that of silicon. So let's park that for now. B might be. Let's see. I know. Let's go to the next. Gallium ars. Oh, you have the answer
yeah,
already.
yeah. Like,
Gallium arsenide has lower intrinsic carrier concentration than that of silicon. Yeah, that's correct.
yeah.
Yeah.
So, like, are you clear why that is?
Yeah, because of intrinsic carrier concentration, right? The
Yeah.
more the carrier concentration, the more the conductivity.
Or you can go for this equation as well. Rho is equal to 1 by sigma. That is resistivity is 1 by conductivity,
Yeah,
right?
yeah, one that I know, correct.
Yeah, that is
Rho is
1 by NIE
conductivity.
mu E
Yeah,
plus mu H.
correct.
Yeah. So based on that, C will
Yeah,
be the answer. Yeah.
got it.
So next is intrinsic semiconductor. It has a band gap. Eg is given to you as 4.9 electron volt. Electron
Mm,
affinity epsilon is 3.6 electron volt.
mm.
Then this is also based on previous week. Nc is equal
Yeah,
to
yeah, this
Nv.
is correct. Yeah.
Then you have to find out phi or work function. If
Yeah, work function is Fermi level to
vacuum level.
vacuum level.
Yeah.
So yeah.
So if
So
you can
now,
draw a picture based on what is
yeah,
given, you will be able to get it.
let me try. Band gap is zero point 0.9, right?
Point 0.9. Yeah.
And affinity is this to Fermi level. Okay, this is the affinity. So that is 3.6 eV. So what is the work function? So 3.6 divided by point plus 0.45.
Yeah,
Yeah,
0.45 plus
3.6
3.6.
plus
And
3.6. Yeah.
yeah, one more thing, we can take like the Fermi level is between these two only because of this condition.
NCF is equal to
Yeah,
NV, right? Because of that.
yeah. Otherwise, we cannot take that because if you remember,
Right.
there is an equation EFI is equal to EV
EV.
plus
Yeah.
half of EG
Mm.
minus 1.2 kBT ln NC by NV.
Hmm.
And when
Yeah, yeah.
NC, yeah, so this term will go to zero, and this, if this is your reference, then it E, like Fermi level is at half of Eg.
Hmm.
Yeah.
Hmm.
Otherwise, if this is not given,
Correct.
something else would be given, and accordingly we have to
Fermi
calculate
level
this value.
calculate.
Yeah.
Hmm.
Yeah.
Yeah. Okay. You remember these equations?
I had to during coursework, so
Yeah, but everything you remember, most of them?
yeah, at least common ones we'll be able to remember. Like Ni
Okay.
value, EFI, then suppose if it's a PN junction, the voltage one. Like very common
Oh,
things. Yeah.
okay.
Actually, there are equations for this NC and VN, like
Yeah,
every, yeah,
NCAV
so
also
those
that
things
also I
are
know, but I
difficult to
think it's
remember. Yeah.
difficult for me to remember. I
Yeah.
don't think I'll remember. Okay.
Yeah.
Doping reduces mobility due to impurity scattering. Undoped gallium arsenide has an electron mobility of this much at 300 Kelvin. After doping, the electron mobility decreases to this much. Find the scattering time associated with the impurities given the effective mass of electron is this much. Okay.
Yeah.
I think there's an equation directly for this also.
Yeah.
Let me search at least the equation. I'm not solving it, but yeah, you want the time.
Yeah.
Scattering time due to
Impurities.
impurities. It is TL is equal to TI is equal to 1 upon pi R C square V TH and 1 into 1 upon T raised to minus 2 raised to T raised to half.
Yes.
Mm,
That means
okay.
complicated ones are not required here. Like one is this one. Mobility is
Yeah, yeah.
ET
Is
by
1
ME star.
upon
Yeah.
yeah, correct. E raised to mobility is E raised to T upon ME star, correct?
Yeah. Now you
That is
got
good.
it due to the electron due to the electron scattering path you have it, right? Like the total
Mm,
one. And the
mm,
second, like suppose you find the first time. So do you remember I talked about one Matheson's rule last week, right?
Yeah,
Yeah.
this one.
Yeah. So using that now the new changed one is 3500.
Mm,
So you substitute the one that you've calculated and find the T due to impurity scattering. Due to lattice scattering, we already found out, right?
mm,
Yeah. So because lattice scattering remains constant, doesn't change, right? This TL value.
mm.
Yeah. So first you find the TL value using this one.
Okay.
Yeah.
New E is to 1 second.
Yeah.
Yeah, understood. Okay,
Yeah.
got
And then
it.
you substitute the second part. And
Mm,
finally you'll get this two, like the substitution wise, it will be a bit complicated.
yeah.
Yeah.
Okay, it's good, but
Yeah, you can, like once I upload the PPTs, you can, like maybe whenever
yeah,
you
go
find
through
time,
once
you
again.
can try solving them out.
Yeah.
So
Next one I do that. The mobility of charge carrier dash as the doping concentration increases. The mobility of charge carrier dash uh, as the concentration increases decreases.
yeah,
D. Yeah.
so this is,
Yeah,
yeah.
just graph. Yeah. Yeah.
So now we'll move on to whatever like we had left out last week.
Yeah. So I have another question.
Yeah, yeah.
Yeah, you finish this and then we go through
No,
that.
you
Yeah.
can ask me. No, it's fine. Yeah. What is it?
That was related to in the practice assignment here, right?
Okay.
On the practice assignment, there is number one. When is the at what level of hole concentration is the conductivity minimum? That's I didn't understand what they're asking there.
At what?
The practice assignment number 3, practice assignment,
I think,
wherein it is not an assignment, it is a practice wherein it's not evaluated. Then
yeah.
what will
So is this the same question?
let me read
Sorry.
that.
Not this
Then
one, not this one.
what is
Just coming there. Like, do they have they given options?
Yeah, they've given options. Yeah,
What are the
you go to the
options?
if you are logged in onto the professor. This
Mhm.
I can share my screen. I don't think, right?
It's okay. Like, is this the what was the question? Can you repeat?
One second, I'll repeat the question itself. I'm going there. Just a moment.
At what Hall concentration the conductivity will be
Yeah,
minimum?
conductivity is minimum.
And the options are like Ni root of mu
And
e.
yeah, 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 yeah.
Yeah, so that is the one that we had left out last week. It's the same thing.
Ah,
Yeah,
correct, correct. Yeah,
yeah.
yeah. Tell me that. I
So,
didn't understand what
so
Hall
basically
concentration.
they are asking what is the whole concentration when conductivity will be minimum, right? So,
Consider electrical conductivity of a P type at load open concentration. It's conductive. Okay, correct. Yeah.
yeah.
What is that? What full concept will be correct? Exactly this question.
So
Yes.
sigma is basically E into N mu E
Hmm.
plus
Hmm.
P mu H.
Hmm.
So they are asking what will be the value of P? P is the whole concentration, right? What is the
Hmm.
value of P such that sigma will be minimum?
Correct.
So, like in basic mathematics, we know that there, like where there is something known as local minima, global minima, all
Local
those
minimum.
things.
Yes. Hmm.
And
Hmm.
in order to find the minimum value of sigma with respect to P, what we have to do is we have to find d sigma by dP and then equate
Mm-hmm.
it to zero.
Okay.
Yeah,
D dp and equals it to zero.
yeah,
Okay, they want at a level of P minimum.
yeah.
Okay, correct. It,
So
yeah.
suppose it was n minimum, we'll have to differentiate it with respect to n.
And yeah,
Yeah, so
so
since they
this
are
should.
asking whole, we have to differentiate with respect to P. So can
Hmm.
you if you remember the basics of differentiation, you can try.
Yeah.
Yeah.
New P is like everything else is constant. Wherever
No,
there is
but
P,
no, but we have to remember that n is also related to p, right?
yeah, N is related to P.
So
Yeah.
it's ni square by p.
S square by yeah, P, correct.
So you have to substitute this n with ni square by p and then
Oh, with
start the
respect to P.
differentiation.
Okay, okay, okay.
Yeah. Can you just try starting to differentiate?
Yeah, I can.
Yeah.
See now. So E raised to Ni square differentiation of this is Ni square by P differentiation is I don't know.
So like suppose if you write e, sorry, e
Yeah, E is an
ni
E
square
into
by
Ni square by
p
P
mu e.
mu E plus E into P nu H.
Yeah, so what you'll have to do is rest all will be constants, right? So
Correct. Yeah.
1 by t will become minus 1 by p square, right?
Ah, minus one by this I've forgotten. Yeah,
Yeah.
minus one by P square. Yeah, this is what I wanted.
So you'll get something like this. Minus 1
Mm-hmm.
by p square here, and here the p will go like differential of x is 1, right? So similarly, if you
Mm-hmm.
differentiate p with respect to p, what
Nu
happens?
H it
You'll
will
get 1.
become.
And now you have to
Hmm.
equate this to 0.
Okay.
Yeah,
So, and in terms of equate this to zero,
yeah.
understood.
And then you
So
have
you
to
need.
write in terms of what is P equal to.
Okay, got it.
Yeah,
Yeah.
can you just try?
Yeah, I can do this. This second. So the denominator is p square, no? If you take the denominator as p
Yeah.
square becomes zero because that side you're equating it to zero, no?
No, this is a plus sign, right? So suppose you take E is equal to minus Ni square by T square
P square
mu E
mu e
plus
plus
mu H is equal to 0. So this will
zero, yeah.
go.
So
So
what?
mu H will be equal
Mm,
to mu E Ni square, sorry, Ni square by
N
P
square.
square, right? Yeah, so your
Mm,
P,
what? How did they put it to the denominator? It became zero, yeah.
yeah. So
Okay, but still.
then you're left with two A plus B is equal to 0, right? A
Okay,
plus B is equal to 0
you moved that. Okay, got it.
minus B. Yeah.
Root of ni, root of, yeah, with the ni comes here.
Yeah.
So new e by new h. Okay,
Yeah. So B will be your answer.
a I think, right?
A mu E by mu H, right? It's
Yeah,
mu E by mu
a,
H. Yeah. In your options, it might be different. Mine might be jumbled up. So whatever is it.
the same there, no? The option. Go to
Oh.
the back. You have the same option there. If you go back, yeah, new e by new h. B. Okay,
Yeah.
correct. Yeah, I thought that is okay. Correct. B. B is correct. Sorry.
Yeah.
Yeah, got this.
Yeah,
Now
and
if
suppose if it is with respect to force, then you will have to convert P to N and then
hmm,
differentiate with respect to N.
split to n, yeah,
Yeah,
got it.
and it goes not only for this equation, for any equation, and if you are asked to find out the minima, differentiate with respect to what you want the minima and then equate it to 0.
Okay.
Yeah,
Yeah, if you can explain me those rules, those laws, Hund's law,
yeah, 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 yeah.
uncertainty law,
Like we had in first class, right?
first class. Yeah,
Yeah. Okay, this part did we do last time?
yeah, this one, yeah.
Okay, fine, fine. Okay. So basically, they are asking. So suppose you have, say, for example, you take a metal, like say carbon is 12, right? So how do
Hmm.
you fill 12? 1s2, 2s2, 2p, etc. And so on, you keep on filling, right?
Hmm.
Yeah. So that is the way in which molecular orbitals are filled with, like when we are using rules of chemistry. So they are
Correct.
asking, whenever molecular orbitals are filled in like increasing order of energy, what principles do not govern the filling? So the answer
Hmm.
what we found was Heisenberg's uncertainty principle doesn't depend.
Not
Rest all
depend.
are important. So
Correct.
we'll go one by one. So first, what is
Hmm.
Pauli's exclusion principle? So Pauli's exclusion principle, the rule statement is that if you're taking say two electrons, so we have an
Hmm.
electron A and we have an electron B. These two
mm,
electrons cannot have the same set of quantum numbers. That is the
mm,
statement. So
mm,
now we'll discuss what is quantum numbers. So quantum
mm,
numbers are basically a set of four numbers.
mm,
So first, do you remember what are these quantum numbers? Like it's from your 12th grade. I think it would have
mm.
been a long time back. There are,
Yeah, long time.
yeah. So there are like four quantum numbers. So first one is the principal quantum number. Then
Mm,
we have the angular momentum quantum number, magnetic
mm.
quantum number, and spin quantum number. So we denote
Okay.
it by N, L,
Mm,
M, and say S. So
mm,
some people say MS, I guess. Yeah,
mm,
ML and MS. So this is the principal quantum number.
mm,
Then this is the, like, either you can call it the angular momentum or you can call it the azimuthal quantum number. Then you
mm,
have the magnetic quantum number and you have the spin quantum number.
mm,
So suppose the Pauli's exclusion principle says that suppose A has a set like 1, 2, 3, 4. There can
mm.
be no other electron having the same set. It has to be something like say 4, 3, 2, 1. It cannot go in the same like A.
Come again. What did you say that A has a set 1, 2, 3, 4?
Suppose
What?
these are four quantum numbers, right? So I'm
Correct.
just taking a random number. This is not correct at all. I'll tell you why.
Mm.
So
Yeah, no problem.
yeah, so this is your N, this is your L, this is your ML,
Mm.
and this is your MS. So one, 2,
Okay.
3, and 4.
Mm.
Pauli's exclusion principle states that if A has 1, 2, 3, 4, B can't have 1, 2, 3, 4. It has to be some another number.
Okay. So A is something that E raised to
No, no,
the.
that is electron A. I'm just naming my electron as A. I'm naming,
Okay,
yeah.
electron A. Electron A has these quantum numbers, then electron
B
B does
can't
not
have
have
them.
that.
Yeah.
Okay, okay. Got it,
Now
got it.
I'll tell you why this is important in filling. So I told that there are four quantum numbers, right? Say like
Yeah.
N, L, M,
Mm,
L, and MS. So
mm.
MS denotes the spin of the electron. In what way the electrons are spinning? It can be minus half or plus half. These are the
Plus
two
half.
numbers
Correct.
like
Yeah.
M can take on. N is
Mm.
like 1, 2, 3, an integer whole number. It actually tells us the shell.
Okay, got it.
Which
Shell.
shell? Are
Mm.
these two clear?
1s2, 2s2, 2p6, and all
Yeah,
those
yeah.
things, right?
That initial part will be there, right?
Uh,
So
uh,
that is the principal quantum number. So the azimuthal
okay.
quantum number, it gives us the shape of the like orbital. Suppose you might have remembered that there is spherical shape, then there is dumbbell
Uh,
shape, all those things.
uh, uh,
And
uh,
so L can have values from 1 till n minus 1. So this is your
okay.
n and it can go till n minus 1.
Uh, uh,
Sorry, it starts with 0, not till not from 1, 0 to n minus 1.
0 to
If it
n.
is 0,
Okay.
it is S. If it is 1,
Mm,
it is P. So it goes on like that.
mm, mm,
Yeah, this is your shell, this is your shape, and now you
mm.
have your magnetic quantum number. Magnetic quantum number tells us the orientation and the subshell, and it goes,
Orientation and subshell.
yeah,
Okay. Mm.
and it goes from minus L to plus L.
Minus L to
Plus
plus
L.
L.
Yeah. So
Okay,
these
got
are
it.
the four quantum numbers. Suppose your electron A has N, L, M, L, and MS in one particular set. The same set
Mm.
cannot be repeated for any other electron.
Okay,
That
got
is
it,
your
got it.
Pauli's exclusion principle. So we can say that suppose this filling is there, right? Each of these
Mm.
electron has a different set of quantum numbers. So it is important for filling.
Correct.
Yeah. So Pauli's exclusion principle is important for filling. That is there. Yeah.
Got it.
Yeah. So next we have the Madeline's rule and the Hunt's rule. So if you
Mm.
remember, we usually fill 1s, 2s, 2p, then 3d. Like instead of, then we have
3s.
3s, 3p.
3p.
It's
Mm.
supposed to be 3d, but what happens is that instead of 3d, we actually fill 4s and then 3d, right?
Why?
That is because of the change in their energy. First, we have to fill lower energy subcells and then go to higher energy. Even though the
Oh,
number is higher, 4s has lower energy.
okay.
Yeah, that is decided by this Madeline's rule and the Hunt's rule. Yeah,
Okay.
Madeline, that person told that it should be filled in such a way that electrons fill energy sublevels of atom, and Aufbau principle states that they occupy the lowest available subshell. Yeah,
Okay.
so that is why 4s becomes filled after 3d. Yeah,
4s fills first and then
3D.
3d.
Yeah, and if you see this diagram, it's like first 1s, 2s, 2p, 3s, then 3p,
4s.
4s, then 3D. Right. Yeah.
No, 1s, 2s, 3s,
Yeah.
3p, right?
Yeah.
Then comes 3p.
Yeah. 3p and then comes 4s. If 3D doesn't come. Here's 4s comes. After filling 3p, we have to fill 4s.
Okay, okay,
Yeah.
okay.
So
And
this,
then 4s to 3d.
yeah, then 3D, then 4p, then
How do
5s.
I know that? How did they come to know that this is the higher energy?
They measured like using some spectroscopic technique and so, or they tried to, what they did was they tried to eject the electrons from these orbitals and they measured the energy, and then they found out that 3D has more energy than 4s. So based on that,
They
they
fill a
derived.
lower energy and then they go for the
Yeah,
higher
yeah.
energy.
So Madeline's rule and Aufbau principle, both of them are important.
Okay,
Yeah.
good.
So only thing that's left is the Heisenberg's uncertainty principle. It is related with quantum mechanics.
Hmm.
So quantum mechanics, if you remember, it sees whatever we see has both wave nature and particle nature, right?
Hmm.
So if it's a particle, we can say that okay, it is stationary somewhere. If it is a wave, it is not stationary, right? So
Hmm.
whenever we are saying that matter has this dual nature, it becomes impossible to pinpoint the location and momentum of any object in space.
Okay.
Yeah. So that is Heisenberg's uncertainty
So
principle.
this is a wave, right? So we
Yeah, we
cannot
cannot.
point. If it's a particle, we would have pointed
Yeah,
it out.
but everything, if like matter has dual nature, and because of the dual nature, we can't predict or calculate exactly the position and momentum of objects. So that is why, like whenever we draw the subshell and everything, we say that that is an electron cloud, right?
Hmm.
So
Hmm.
instead of drawing a point, it is like a cloud, and anywhere within the space, you have the probability of finding that electron.
Hmm.
Yeah,
Hmm.
these are like very small numbers, maybe nanometer or less picometers or angstrom, like very small numbers. But
Hmm.
physically, it won't be at a single point in space. It would be a
Got it.
region.
Okay. Only because it is treated as a wave.
Yes.
Assume,
Yeah, because of the
assume
dual nature.
dual nature.
Yeah.
Okay.
So then,
It is treated both as a particle and a wave. That's what you mean by dual
yes,
nature.
yeah,
So if it was a particle, then you could have,
pinpointed the location, no issues.
yeah. Then
But
if why do they not assume it as a particle and then pinpoint it?
like that will go to theories of diffraction interference, hardcore physics.
Okay.
People came to know by studying these like phenomena that nothing is actually a particle, it is both wave and particle. That goes to
Okay.
like hardcore quantum mechanics.
Okay.
Yeah.
Okay.
So now if you see, we understood that Hunt's rule is important, Madeline's rule is important for filling. For
Hmm.
Heisenberg is like prediction of position and momentum, right?
Hmm.
So it is not important for filling of molecular orbitals.
Okay. Got it.
Yeah.
So
Like,
Pauli said that quantum numbers, Madden energy rule is that it
yeah, Hunt's
fills
rule is
into
also,
more
yeah,
energy.
Hunt's rule is this one. Like, so let me clear all this. Yeah. Suppose you have one, 2, 3, 4, 5, 6, 7 electrons are there.
Hmm.
So you have S has two boxes.
Yeah,
Then,
it will fill an opposite
yeah.
spin.
Yeah, P has like, this is S, this is S, this is P. So this
Hmm.
is 1s, 2s, 2p. So actually how we fill is this is one electron, this is another electron, this is one electron, another electron. If you are following the same rule, we would have gone on filling like this, right?
Hmm.
And then it would begin like something like this. But this is wrong. We can't fill it. So
Hmm.
these boxes too have energy. And first we have to singly occupy them before doubly occupying them.
Okay.
Yeah,
First, everything is occupied singly,
single
and
then
then
doubly. So what we go on doing is suppose we have three electrons left, it should go like this. We
it
cannot do.
starts again filling.
Yeah,
Okay.
it cannot go on like this. This is wrong.
Oh,
That
it cannot fill like two
two first
boxes
and
first,
then one next.
then
It
one,
can't do
one,
that.
one. Okay, okay, okay,
Yeah.
okay. First, it fills one, one, one everywhere, and then again, once everything is filled, then
Then
it
it comes
starts filling.
back to the counterpart.
Okay, okay.
Yeah.
This I did not. Okay,
So
good.
that is the
Good.
Hunt's rule. So all of these are important in filling. Like Heisenberg's uncertainty principle is not important in filling.
Okay,
Yeah.
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 Got it. Thank you. I
Yeah.
think I learned something.
Yeah. And if you are interested in quantum mechanics, like you can start reading up. It's like an ocean. It is interesting to read,
Yeah.
but difficult, but very interesting.
Oh, is it? No, I'm done, I think, with that age. But yeah, nevertheless, if I finish this course, I'll go and read that.
Yeah.
Yeah.
Like,
I'm more interested in application. So,
yeah, but the thing is, if you like start understanding quantum mechanics, we'll be at the point where we can visualize. Okay, this is the reason why, like atoms get arranged in so and so format. It's all related to energy. That like you can get a lot of answers to why everything is as we see it.
yeah, 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 I
Yeah,
know.
yeah.
Mm.
So yeah, that's I think it's
Yeah, I was interested in this course because I wanted to really understand electronic materials
yeah,
and how fabrication happens and all those things. That was the whole motive
motive.
behind
Yeah,
me taking this course. Yeah.
yeah, yeah. And
No,
have
but I
you
wanted to
registered
go
for the
through.
examination or are you
Yeah, yeah, I
planning?
have registered.
Yeah, yeah,
Yeah,
okay.
I have registered. I don't know if I will be able to remember this equation. I'm just waiting for the good news that all the equations will be
Yeah,
there.
but usually in the examinations that happen in college, the faculty gives, so he might insist, or even if they are not giving till now, I can ask him whether they can like try to force and make an exception this time.
Yeah, otherwise it's difficult to remember all
Remember
these
all these
equations.
things,
Really,
yeah,
hardly impossible.
yeah.
For me at least. I don't know for others, but
No,
for
but
me, it
like it's
won't
okay
work.
if there are only few, but it goes on piling up with each week.
Yeah, it's piling. No, you have to have every other equation to solve it.
Yeah, so yeah,
I
it's
don't know.
difficult.
Let me know how it happens.
Yeah, and along with the equations, you'll have to remember the values of constants as well.
But constants and all, yeah, I cannot remember now only. You've told me so many times, I'll not be able to remember
Yeah.
that.
And I
Single
think in
constant.
semiconductor, mostly the things you come across is one is Boltzmann's constant, and then
Yeah.
you have mass of electron, energy of electron. These are
Yeah,
like,
but with
yeah,
that and equation, lot many things.
things,
I think
yeah.
they should allow an I think open book in MBAs they have an open book exam.
Okay.
That's how you should
Like
do it.
open book in the sense you'll be allowed to
You take
carry.
the textbook and go to the exam
Okay.
and you solve the paper.
Okay. It's an
In
NPTEL
MBA, it's
course.
all open. You can take how many ever books you want. You can take your laptop also and
Yeah, like
then also.
open books exams are there, but for
Yeah,
NPTEL, there are no courses which offer, I think.
yeah, I know, but
Yeah, yeah, yeah.
it's not that. I don't know. I just found this course and professor was teaching well, so I just went ahead and enrolled for the first one, and then I thought this is a linked course. I got a pop up for this, and then I said, okay, let me
Yeah.
go ahead and try.
And in the coming weeks, if possible, try to at least, just if you can't go through the entire lecture,
Yeah, yeah,
just,
yeah. I'll go and come through the videos. I
yeah,
usually am a week behind.
yeah. But towards the end, it becomes difficult
Yeah, I know.
because, yeah,
I'll go. I know it's starting to become difficult.
yeah,
So yeah.
transistors, MOSFETs, JFETs, this, that, it goes on becoming very complicated towards the end.
Mm.
So if you don't know,
Yeah.
like, the basic things, it would be difficult for me to discuss the questions also. Like, explain,
No, no. I think
yeah,
till extrinsic semiconductors, I know really well.
uh-huh.
I think I'm okay with that.
Yeah.
I have to go ahead and solve problems, but yeah, I have to do that junction now.
Yeah, yeah.
That's where I will
Yeah.
really
Even
struggle.
junction
But
part,
I'll
I
get it.
think you'll be able to fit it. Like it would be good. But coming to the transistors, this, that, yeah.
Transistor MOSFET, yeah, that's a little bit of
Because
issues.
explaining them from class, scratch during the class will take up a lot of time. Then we won't get time to
No,
solve
I'll read and
problems.
come.
Yeah.
I'll read and come for that.
Yeah.
That I will read. I'll make sure that I go through the videos at least.
Yeah.
Okay,
Yeah.
thank
So,
you.
yeah.
Thank you
Thank
so
you
much.
so
So
much
you
for
are doing
joining.
your PhD or you have finished your
No,
PhD?
I'm in my third year of PhD.
Oh, PhD doesn't have a year, right?
Yeah,
It is
but
going.
they'll provide money only for 5 years. So we say,
Uh,
yeah. If after
so you're doing your PhD in electronics.
No, actually, I work on a completely different field. I work in polymers.
What polymers? Oh,
Yeah,
what polymer?
like
Uh,
polymer composites,
X6.
metal oxide polymer composites.
Okay.
Yeah, the thing is, I had this course during my coursework. So, and
Uh,
some part of it is important for me, like the photocatalysis part, solar spectrum part. So, I
uh,
took this course and I somehow liked it, and now I'm pursuing it as my TA work. Yeah, my
oh,
research is not at all related to semiconductors.
so you learned this, but you are also not a electronics engineer,
No,
right?
no,
You
no.
are polymer, then you are most probably chemical or
I was
mechanical.
initially my BTech was in mechanical, then I shifted on to materials in my MTech.
Material science
Yeah,
engineering.
yeah, and now
Okay.
into polymers and
Yeah, material science is closely related. I think
yeah,
lattice and all is there,
yeah,
right?
like we'll be able to like understand polymer basics with my materials background, but not with the mechanical background.
Yeah, yeah, mechanical is something
Completely
everywhere.
different. Yeah,
Everywhere. It has all the subjects.
yeah, yeah. But
Little
yeah,
everywhere.
chemical would be the most like what most close enough thing.
No, materials, you have done material science. No, material science should cover that, this. lattice and all those things, right?
Yeah, but the thing is,
Application.
when you're studying material science, like there are like two broad categories. One is conventional physical metallurgy part where people work with alloys, steels, and all those things.
Hmm.
Then
Yeah.
comes the
What
soft
diagram is
mat.
that? I
Yeah,
just remember that diagram.
yeah, iron carbon phase diagram, all those
Air
things.
carbon diagram. Yeah,
Yeah,
yeah. You take and
yeah, that is one. It's like completely
yeah.
different way or a branch, and
That
then
goes to steel
yeah,
industry,
and we
probably.
are a section where people deal with soft materials, polymers, semiconductors.
Yeah, yeah, polymers. I think
Yeah.
I deal a lot with polymers from an application standpoint, from not a mathematical
Okay.
and all those things.
Yeah.
Yeah, more on the application. That's what I was looking for, courses and application standpoint. How happen, and do they do any course wherein how a chip is designed, all
I
that? Something
don't
is there.
think so. That would like be very specific, right? And I think people trying to like people usually who take the NPTEL course, they go for it because they need to understand fundamentals. But if you are designing a course specific on a specific application, it would become too specific, and people feel that there won't be much of an audience for that.
Mm. Okay,
Yeah,
okay, got it,
because it
got
would
it,
be useful to only a very few, right?
got it.
Yeah, but yeah,
Okay,
yeah,
thank you so much
yeah. Thank you
for
so
your.
much for joining. Yeah, we'll meet next time. Thank you.
I'm the only one joining
Yeah, yeah,
regularly.
yeah.
Okay, I think
Yeah.
the rest all are studying and probably working for the marks.
And the thing is,
Hopefully,
like since the videos are uploaded, many people feel that they
yeah,
need not.
probably
Yeah.
need not. Yeah, thanks.
Yeah. Thank you so
Thank you
much.
so
Yeah.
much.